So after we end up looking at the subatomic particles, that's going to lead us to some way to categorize every one of those atoms. Thus, we need a tabular arrangement called the periodic table. Tabular meaning table, get it? Okay, so it's nothing more than a configuration of all of the known atoms. Also, notice that it's constantly growing. This picture was taken before we had a number of atoms added. If you look up a more recent one, you'll find a bunch of gray ones here. They tend to be gray because we don't know a lot about them other than we could make them for a split second in a lab by colliding particles together. Protons together, really. And so most of them only were sustained for very short periods of time, and we don't know most of their properties. The rest of them tend to go together very, very well. The main organization tool, though, is how many protons it has, thus its atomic number. That's why they're labeled 1, 2, and so on and so forth. But it shows so much more. We'll be looking at that in this section. Do note this point, though. There are no isotopes or ions on the periodic table. The periodic table is designed to represent a stable, neutral form of the atom. That doesn't mean some elements, I'm looking at uranium, aren't somewhat radioactive on their own. But this is the most stable and neutral an atom will be. First thing to be able to recognize is we don't like to call them rows and columns. Rows we actually call periods. Columns we call groups. It's just a unique reference to the different things on the periodic table. It does have some purpose because you will also find out things in a different period have different energy shells. Things in a group have different properties as well. Sometimes groups are also called families, which can be a little bit troublesome, but they try not to do that because basically all of these groups are also in about the same family, but sometimes they'll refer to it in books. So don't be alarmed if you hear a group called a family. It just means a column. Period, though, that's the rows. Now, even the most basic periodic table should have certain information facts that you need to get from every little cell. These right here are what you should find on even the most basic periodic table. Notice it's not colored, it's not fancy in any form, but you should be able to know what the name of the element is, right? You need its atomic number, meaning how many protons it has. You need its atomic symbol. And I don't know why, but let me go ahead and specify, yes, the symbol, it does matter, caps or not caps. The first letter is always cap, the next are not. That's part of the symbol. Okay, and then you need atomic mass. Atomic mass, as I might have mentioned before, is made of both neutrons and protons, and so it's a quick way to be able to figure out how many neutrons and how many protons. Notice, though, that it's not a perfect number. We'll discuss that a little bit later. Okay, so let's take a little bit closer look at each of those different aspects of information you're getting from the periodic table from each cell. First off, let's look at the atomic mass number. It is considered the sum of protons and neutrons, even though I did point out that it should be a whole number if it was exactly one AMU and 1 AMU. The truth is, the way they calculate it is based on averages because we have to do mass numbers of them. And so what you actually need to do is you need to round it to the nearest whole number, and this will work out pretty well with elements on the periodic table. With doing that, you'll be able to subtract the atomic number, which is the number of protons, from the atomic mass number, and you'll get the number of neutrons. Fairly simple. Here's a little formula if you don't know how to do that. We also can actually get the number of electrons out of that cell. Why? Because we said that all the elements on the periodic table are neutral. If they're neutral, that means you have to have an equal number of negative charges that you do to positive charges. The atomic number tells us the protons, right? So if that's how many positively charged particles we have, then we need the same number of negatively charged things, which are electrons. That would mean that the number of electrons is also the same as the atomic number for a neutral atom. Notice this does not work for ions. If you change the number of electrons, you create an ion. Energy levels. Now, you might not have noticed that, when we were talking about the little cells, because that's actually more known if you look at the row or period that it's on. It does have that information though. So each period means how many different shells or shelves, I've heard them called, that electrons sit on. Okay, if you've ever seen, this is a Bohr model of an atom. We're going to learn how to do these a little bit later in this unit. These represent those different shelves, and you can tell the number of shelves simply by the row or period that it's on. Remember, we're supposed to call it periods and not rows. But the periods aren't the only thing that teach us things about the electron configuration. It would be the groups that they're in, because that'll give us an idea of how many valence shell electrons. If you're not familiar with that, valence electrons, those are just the electrons in the outermost shell. So we said the periods give us the number of shells that we have. Notice you can only go up to 7 for those shells. But then the columns, the groups, will tell us how many electrons we should be finding in the outermost. Also notice that it does not hold true for our transition metals, but for everything else, we can figure out that there would be 1 here, 2, 3, 4, 5, 6, 7, and 8. Okay. In my opinion, this is where information starts to get a little bit more difficult, because in each of those energy levels, there is a max number of electrons that it can hold. Now, that's for the energy level. That's not necessarily the same thing as an orbital. We'll find out later after this unit. For this unit, we're looking at things in the Bohr model where it just has energy levels. The reason these fluctuate so differently, notice that it's only 2 in the first one, 8, 18, 32, 32, 18, 8, because you actually find out there's 4 types of orbitals that can make up a different shelf. And the way they fall into those depends on how many can be in there. They're called the S, P, D, and F orbitals. And they actually have different shapes and can hold various numbers of electrons. It's much, much more complicated, but right now we're thinking about it in the simplest form. So Bohr model uses only energy levels, and this is the exact number of electrons that can fit in each one of those. Notice though, it is all even because they like to make electron pairs. Now, with that information of how many electrons, valence shell electrons, we can also figure out its oxidation number. Oxidation number sounds a little funny, but all it is it's the tendency of the charge that an atom will take when it becomes an ion. And so this makes sense because it's that valence shell that's going to change its number of electrons when it becomes an ion of either a cation or an anion. And so we know that if it has a few number of electrons in that valence shell, then it's going to become positively charged. It's going to get rid of electrons. But if it has a lot of electrons, like these here in the valence shell, then it's going to tend to pull in electrons and become negatively charged and be an anion. Notice our noble gases, they don't become an ion at all. That's because their energy levels are already filled. Their valence shell is filled up. They don't want to give away or take in. They want to stay perfect just as they are. But then we can get into much, much more. So if you look, this table is absolutely amazing. So not only did we find information about each atom in the little shell, not only are they listed in order of protons, not only do they tell us our valence shells, the valence electrons, or the number of shells that the atom has, electron shells, it also starts to tell us properties about it. For instance, it's organized by nonmetals. Notice where hydrogen is, though. It's a little bit odd. We'll discuss that in a little bit more depth later when we're doing ionization. It has metalloids and metals. Now that would be enough, but yet there's more. Because in the periodic table, it also groups elements by like properties. And a lot of these create what we like to call a family. That's why I said sometimes they call the groups families. So you have your alkalis and your alkalines. You have your transition metals, your rare earth metals. You have your metalloids, nonmetals, your halogens, your noble gases, and your other metals. Other metals can be a little bit confusing at times, but that's just because they tend to have multiple properties from where they stand. And even all of this, there are still more trends to the periodic table. So we're going to have to take a whole nother video just to look at a little bit more of the trends that you find here. Hope that helps for this time.